All right, so 6.3. We're going to be talking about the definite integral again. We're going to be really talking about the definite integral and using it for quite a bit of this chapter. So remember in 6.2 when we defined the definite integral to be the net change of the antiderivative. So we're kind of doing a different, well not kind of, we are doing a different definition today of what the definite integral represents and what we can use it for. So the first thing we want to have the idea of, and you've read this in the book, but this idea of area under a graph. So when we say area under a graph of, let me just use the shift key, it'll be easier for me to draw lines. When we talk about the area under the graph, what we're talking about is if I have a function, f of x, and it can be negative, but when I talk about the area under the graph, let's say it does something like this, from, I don't know, let's say a to b, we're talking about that area between the graph and the x-axis. Okay, so in this case where I have drawn this, the area, if I'm talking about the area under the graph of f of x, and this is f of x, okay, and I want to talk about the area underneath this graph between a and b, it would just be this area, and it's bounded by the x-axis. So there's a nice little, like box that I'm sure you've already copied in your notes, defining that for you about the area underneath the graph. So I hope that makes sense. That's just to kind of get the idea of what we're talking about here. And so the big conclusion, and you saw this in Theorem 1 of this section, and I'm not going to write this out in detail like they did in the book. You should in your notes, though. It says if f of x is, so I'm just going to do this a little shorthanded. Let's let f of x be continuous and non-negative. Don't you wish a lot of things in life would be non-negative? Keep it positive, right? So non-negative just means it's positive. It could hit, the reason they say non-negative and not just positive is because it could be 0. That's okay if it comes down and grabs the x-axis. So let's let f of x be continuous and non-negative on when x is between a and b. Okay, so I'm just kind of paraphrasing the theorem. This is not, this bothers me a little bit because it's not super formal, but you can write that in your notes more formally, how they have that. So then what this is saying, and this is kind of a big deal, is they're saying that the area underneath the graph, which I am just going to note today as a capital A. So in this lecture, whenever you see a capital A, I'm going to go ahead and assume that you understand that when I'm talking about that, I'm talking about area under the graph. This is the area under the graph of f of x, from a to b. Okay? And that, of course, bounded by the x-axis. So this is a pretty big deal because look at what we're saying about this area. We're saying that the definite integral gives me the area underneath that function from a to b. It's a pretty big deal. I'm not going to lie, this is a pretty big deal. Might not seem like a big deal to you, but as a mathematician and as a calculus teacher, this is a pretty amazing result. And we're not going to do a rigorous proof of this. If you were taking a regular Calc 1 and not a business calc, I would prove this for you. But for business calculus reasons, we don't really need to get in that deep because probably not going to take any higher level math after this unless it's economics or statistics. So I just want to kind of show you an example, and we'll just stay on this page. And this is not a proof, but it's going to kind of show you how this is true. And then I want to do this example, one more example, and then that's pretty straightforward, I think, of what we mean by the area underneath the graph, and I'll let you go from there. Because I'd like to spend a little bit of time on this idea of Riemann sums. So the function I want to look at is I want to find the area underneath the graph of f of x equals 2x over the interval 0 to 2. Okay, and the reason I chose this function is because this is a function that when I look at the area, when I look at the area, it's actually in a shape that we are familiar with, and we know from geometry that we can actually find the area of. So I want to show you kind of like, yeah, this makes sense that the area of this function, is a triangle. So 0 to 2, at 0 we're at 0. At 2 We're at 4. Okay, and so this is my graph, and I want to find the area underneath this. So I'll just kind of draw a dotted line. Ha! You should pretend that that's straight. And I want this area right here, which if you notice, right, is just a triangle. So this, oh my goodness, Sarah. Wow. My 5-year-old would be so disappointed in me and my drawing skills here. So we're looking at that graph right there. So clearly we know that the area of a triangle, right, of course you remember this, is half the base. What's the distance of the base here? It's just 2 times the height. What's the distance of the height? Well, it's 0 to 4, so that's just 4. So it looks like the area of this triangle is 4. And I didn't need calculus to do that. But it's more fun to use calculus, so I'm going to use calculus. So let me show you that this is actually going to work. So I'm going to go from 0 to 2, because what does this theorem say? That the area underneath the graph of f of x from a to b can be found by using this, by using the antiderivative and the definite integral. So how do we evaluate this? Antiderivative of 2x is x squared, evaluated from 0 to 2, and I bet you're excited. I know I am. Actually, my heart is racing just a little bit faster. I know that's really nerdy. And then what is 4? What is 2 squared? It's 4, and 0, of course, is 0. So if you notice, we get the same 4 that I knew I would get over here. Okay, so you're probably thinking, well, Sarah, this is stupid. I know that, well, no, you're not ever. You're never thinking that. I'm like, well, Sarah, I know how to find the area of a triangle. Why do I need calculus to help me find the area of a triangle? That's silly. Okay, well, what if we don't have something like a triangle? What if we have something like this? Oh wow, that I did not expect that to be quite so large. One second here. Let me get rid of that. Okay, that's much better. We're not taking up the whole screen here. Okay, so you said, well, Sarah, you know, why do I need calculus to evaluate the area of a triangle? Well, you don't need calculus to evaluate the area of a triangle. I understand that. But what if we have something where we have an area that's not something nice like a triangle? So look at this example I have for you. This is a function. This is the cubic function that kind of curves, like it kind of looks like a triangle, but it's definitely not a triangle. And I want to find the shaded area that I have for you, that I've shown you here. So first of all, let me tell you that the graph of this, or the function, this pink graph right here, is given by the function x cubed. Well, let me tell you once I actually make sure. Yeah, x cubed plus x plus 5. So the reason that the integration helps us is, and we're going to see later on in mathematics, or in this class, why we even care about area underneath the graph and what does it tell us. But for right now, we're just going to get some examples of this and use some of this. So if you see here, I can actually find the area of this kind of weird looking shape, right? This shape's like goes like this and then comes up. It kind of looks like Idaho or something. This weird Idaho shaped thing. So I don't have anything in geometry that lets me find the area of that, but that's why I use calculus. So to find the area of this, I know I'm going to integrate the function because it's the area underneath the graph. Whatever function you put in here, that's the area we're going to find under that graph. Okay, and then what are we going to integrate from? Well, my smallest x value here clearly is -1 all the way up to 1. So my bounds then, oh, not -1, are going to go from -1 to 1. Good. And so here we go. Let's take the antiderivative. That would be 1/4 x to the 4th plus 1/2 x squared plus 5x. I'm going to evaluate this whole thing from -1 to 1. So I think actually this one will be pretty easy to do. Let me show you how we'll do this. So I'm going to plug in a 1. Obviously, 1 to the 4th is 1. 1 squared is 1/2. 5 times 1 is 1. And then I'm going to subtract parentheses. Now if I put the -1 in, if you put this in your calculator, make sure you put that -1 in parentheses. When you take a negative and you raise it to an even power, it becomes positive. So just again get a positive 1/4, a positive 1/2, and then I get a -5. And then making sure these parentheses, right, because I'm subtracting that whole thing. That's a pretty big deal because this guy actually becomes pretty nice. I take the negative through, I get minus 1/4. I made this problem up. And I am very, very surprised that the area became that nice, that we just got 10. Everything else cancels. The 1/4 cancel, the 1/2 cancel, and we just get 5 plus 5, which is also known as 10. So that's pretty neat, right? I'm just imagining that you're just amazed by that. Like, Sarah, I've been waiting my whole life to figure out how to find the area of weird curvy shapes like this, and now I know, and now I'm happy. So I'm glad I could do that for you. Good. All right. So that's the first part of this section, is this idea that the definite integral. So we have two things for the definite integral now, right? So I know the definite integral from a to b can give me the net change of my antiderivative, capital F, okay? And now I'm being a little lazy here. This also can give me the area, not under big F, but under lowercase f of x from a to b, okay? If I got 10 here and I got 10 here, it's the same thing. We just have to look at the context of the problem to know which one it means, right? Does it mean net change, or are we talking about area from A to B? All right, good. The other big thing in this section, and you know, I say it's a big thing, and it is. We're gonna see Riemann sums quite a bit as we move forward. You know, I think I assigned like 2 Riemann sum problems. But the idea here, and I don't really love the way your book does this, but it's fine. I really think they should have introduced the Riemann sums first and then I'd done the area, but that's okay. I didn't write the book, so what am I complaining about? So this idea of Riemann sums. So we're going to come back to this area problem again. Okay, and basically we're going to talk about maybe how this area problem even happened and what this Riemann sum is and what does it have to do with the definite integral. So again, I'm gonna say I'd like that to be a different color. I'm gonna have some function. Maybe it does something like this. Again, it's a shape, right, that I can't easily find the area of if I want to find the area underneath this. So let's say I want to find the area between A and B. Oops. So I want to find, we'll just go ahead and do a straight line from A to B. Okay, and I want to find that area underneath the graph. Well, the way this all started, the way they even found out that the definite integral was the area underneath the graph, is they looked at this idea of approximating the area under a graph using shapes that we know the area of. So like that triangle one, I know the area of a triangle. I know the area of a trapezoid. I know the area of a rectangle. And so what we're going to use, Riemann sums, and I know you've read through this, but I'm just going to talk about this kind of in plain English here, is what we're going to do is we're going to split up the interval from A to B into some subintervals. Okay, and what we're going to do is we are going to estimate. So I have 1, 2, 3, 4, 5, 6, 7 subintervals. And what I'm going to estimate the area here by just putting in rectangles. Okay, so if I put in rectangles, and I'm going to, in this, the thing here is I'm going to look at this first subinterval right here, right? So this is my first subinterval. And I'm just going to grab the left-hand endpoint. I'm going to draw a line up to the function. I'm going to, to the function. I'm going to come straight over, and then I'm going to come straight over, and then I'm going to draw a line down and to the other part of my subinterval. This is what a Riemann sum is doing, okay? So I have this rectangle, okay? Look at this rectangle. So what is the height of this rectangle here? Well, based on how I did this, let's just call, I don't know, this first point right here x sub 1, okay? And I'm going to, this is x sub 1, this is x sub 2, it's some x value, x sub 3, x sub 4, x sub 5, x sub 6, and x sub 7. I don't need to label this guy because I'm using the left part of each subinterval to evaluate this. Well, the height of this rectangle right here is f of x sub 1. And you saw this in your, when you read through this. Let's look at the next rectangle. Okay. So this next rectangle, again, I'm going to start at my left-hand endpoint, so this f of x sub 2. I'm going to come up and grab the function. Okay. Then I'm just going to come over a bit, and I'm going to, I would normally come down, but with this program it's going to work a little better. And I'm going to come over. Okay. Again, at x sub 3, I'm going to come over. I hope you're as amused. Why did I do 7? Oh my goodness. I should not have done 7. I should have done like 2 rectangles so that you didn't have to watch this. Grab the function. Okay. Come over until I get to x sub 4, and then I'm going to come down. Again, grab the function. Start at x4. I'm going to come up, grab the function, move over, and then come down. Why am I doing rectangles again? Because they're easy to find the area of. So what we're doing now is we're doing an approximation of what the area is underneath this curve, okay, using shapes that we know. At x sub 6 again, gonna come up. I'm finding this amusing. I'm gonna come up, grab the function. That's gonna determine the height of my rectangle, and then I'm gonna come down. And finally at x sub 7, I'm gonna come up, and I don't have to use left-hand endpoints. I could have used right-hand endpoints. I could have done midpoints. I'm gonna do one for you where I do a midpoint. Okay, and come down. So look at this. Ooh, that looks actually kind of pretty. So if I look at this, if I took all of these areas of these rectangles and added them all up together, okay, look at what I am missing. So is this a pretty good approximation of the area underneath the curve? Well, my only error really is right here. Right here. I have a little bit over here. I'm a little bit over here. I'm quite a bit over here. Right? A little bit over here, and I'm a little bit under here. But if you notice there, do you see those gray, where I colored in kind of that gray? That's the error, but they might kind of undo each other. And how could we get an even better approximation of the area underneath this function? I could do more rectangles. So they do a nice picture in your book on page 311. They do a pretty nice picture of showing you if I have more and more rectangles, how it's easier to see that you get a better approximation. So my area then, again, I'm going to let A just be the area underneath the graph. Okay, it can be approximated by, well, let's look at what would the area of this first triangle be right here. Well, I know the height. How do we find the area of a triangle? Base times height, right? So I know the height is just f evaluated at x sub 1. And the width, if you remember in your book, the width, well, these rectangles are all of the same width. So I'm going to take the length of that interval, which is b minus a, and I'm going to divide it by the number of rectangles I have, where n equals the number of rectangles. Okay? So this is delta x. So each one of these little things here are delta x. Or if you've seen that triangle before, we call it delta. It just means a change in something. Delta x. So same width for each rectangle. So if I want the area, what I'm going to do is there's the area of that first rectangle, right? How do I find the area of this second rectangle right here? Well, I would take the height of it, which if you look at this, what is the height at right here? This point right here is x2 comma f of x2. Okay, so that height then is f of x sub 2 delta x plus, and I'm not going to write all of them, that's why we love the dot dot dots in mathematics, f of x sub 7 times delta x. And that's an approximation of the area. Okay, so that's that whole discussion on page 311. And this right here, my friends, is what we call a Riemann sum. I hope that helps explain that page a little bit, because I know that sometimes reading mathematics is not the easiest thing to do. Okay. Now, what we want to do is we want to get a better approximation of it, and in this next page, what they talk about, oops, let's clear this guy out really quick. They talk about if you get an infinite number of these rectangles in here. So I'm going to use more and more and more rectangles to get a better and better approximation. Well, I still have the distance A to B, but if I'm going to do like 10 rectangles or 100 rectangles or 500 rectangles, what is that going to do to the width of each rectangle? It's going to have it get super, 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 super small. Okay? So what as we get more and more rectangles, what we see is that the actual area of this, now notice how I put an equal sign and not a squiggly sign. The squiggly sign, remember, is that's an approximate area. So I'm going to put equals, so the limit, we bring in a limit. As the width of each rectangle goes to 0. That means I get smaller and smaller rectangles, which means I get more and more of them. Or we could say as n goes to infinity. Okay, either way. The area actually equals the heights of these rectangles plus dot, 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 plus f of x sub n, all times the width. Because they all have the same width, right? So if you look back at here, what do you notice is, oops, oh, calm down. What do we notice is common, oh wow, to each of these is the delta x. So all I did was I brought that delta x out. I just factored that sucker out of there. All right, and so then, so this is the area, and then the kicker to this is, what does this all equal? It also all equals the definite integral, which we kind of already know, right? I mean, we saw that before, but it's a pretty amazing result that these Riemann sums, if we just put a limit in front of it, we actually get the area underneath the function, which means that is actually equal to the definite integral. Oh my goodness, this is a long lecture. Let's do one example, and then I imagine you're about done. I could keep going, but I understand. So what I want to do is I want you to use a Riemann sum. So this is going to be very, very similar to what's going to be due on your homework. So I want to see you draw, you know, on your homework I want to see you draw a picture, I want to see you draw the rectangles, all that good stuff. So use a Riemann sum and 4 rectangles with height. I'm just going to put with midpoint, and I'll explain that. I'll just put midpoint selection to estimate the area under f of x equals x squared from -2 to 2. Or, oh, I probably should have put over the interval -2 to 2. Okay. I'm going to erase some of this right here. And I'm going to just show you how to do one of these. Okay? All right, so here's what we're going to do. So I want to use Riemann sum and 4 rectangles with midpoint selection. So what I mean by midpoint selection is I'm telling you I want you to use the midpoints to determine the height of the rectangles. Okay, so let's draw a picture first. I want to see this picture in your homework. I want to see you actually graph the function. I want to see you draw some pretty rectangles, all that good stuff. Okay, so from -2 to 2, so 1, 2, 3, 4, so x squared goes through 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. We know what this looks like. This is a parabola. Oh, this stylus, oh man, is not, I need to really like sit and practice doing this. Oh, and maybe I should practice it not when I'm actually lecturing. I want to tell you thank you for being patient with me, but maybe you're not being patient with me. At least I don't know. I haven't seen any nasty comments, so that's good. All right, so here's what I want to do. So here's my intervals. So basically I want to go between -2 and 2. So let's figure out what delta x is going to be. So I'm going to take b, which is 2, minus a, which is a -2, and divide it by the number of rectangles I want, which is 4. So I get 4 over 4. Oh, this is pretty nice. So what is the width of each rectangle? It is 1. So I'm going to have a rectangle here, 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 and here. Okay, get rid of those for a moment. And now when we do midpoint, midpoint's kind of fun to do. So what you want to do, let's do pink. So I'm going to take the midpoint between these two. I'm going to come up and I'm going to grab, so I just went straight up from the midpoint, if you see that. I grabbed the height of the function, and then I'm just going to make a horizontal line, okay, across the interval, because I know my interval is going to be 1 by 1, right? Because that's what this guy told me right here. Same thing here, so between -1 and 0, I'm going to take the midpoint, I'm going to come up and grab the function, I'm going to make a nice, that's the height, and I'm going to come left and right and come down at the middle of my interval. Same thing here, take the midpoint, grab the function, come up and down. You need, oh, and sorry, that's a little tilted. Here, grab the function, midpoint again. Well, it should be the same as this one. Midpoint again, come over, and then come down. So, your graphs do not have to be perfect. Obviously, mine are not. But if you look at this, so this is, now clearly this is going to be, right, we're going to have a definite overestimation and a definite underestimation, because where do I actually want to find the area? I want the area from here to here, right? And so this, what I'm doing here is I'm missing a bunch of stuff right here, but look at, I'm overestimating here, so it might not be too bad. Here I'm missing some of the area right there, but I'm overestimating here, so it might not be a horrible one here. All right, so let's go ahead and do this. So my Riemann sum again, I'm going to take the area equals, let's look at this first one right here. What is halfway between -1 and -2? So that would be f of a -1.5 times the height, which is just 1. So I can just do plus. Okay, let's do this one now. That's just a -1/2, so -0.5 plus, let's do this one. Between 0 and 1 is 1/2, so I would just do 0.5. And then between these two here is 1.5. So plus f of 1.5. And then technically this whole thing, right, those are all the heights, is being multiplied by the width of each rectangle, which is just 1. And then this is where you get out your calculator and you determine this using your calculator. So how do I evaluate, again, f of a -1.5? Well, what is my function? My function is x squared. So this would be a -1.5 squared plus a -0.5 squared plus 0.5 squared plus 1.5 squared. And there's going to be some repetition here because we're, you know, it's the 0.5s don't really matter. So 1.5 squared plus 0.5 squared. Oh, look at what we get. This is awesome. We get 5. Okay, so that's an approximation, right? So what does that number mean? It's the area of all of these rectangles right here added together. Okay, that's what that means. And I think in your homework, I gave you 2 problems like this where you do left endpoints and right endpoints, so it's not as hard maybe as the midpoints, but I expect to see you draw the graph. I expect to see you sketch the rectangles and then show me your work. And just for fun, just really quick for fun, what is the actual area? Well, I could find the actual area by integrating from -2 to 2 of x squared dx. Oh man, I'm almost at a half hour. I hope you're still with me. Which is 1/3 x cubed from a -2 to 2, which is 8/3 minus a -8/3 when you cube a negative. So I actually know that the actual area of this guy is 16/3, which if you look at that, right, is 5 1/3. So we actually aren't off too much with the 5. That's a pretty good approximation using only 4 rectangles. Again, the idea here is if you use more and more rectangles, you are going to get better and better approximations of the area. All right, well, that was fun, you guys. Good luck on your homework, and please holler at me if you have any questions.